the upper wall of the cylinder within the direction of increase here in the projection for the phi angle deflection from the x-axis, and z from the height of the cylinder. Right, this is what we've been considering, how to define, for example, the position vector. The position vector would be that this vector plus this vector, so together it would be rho and rho plus z and z. Then with velocity being the first derivative of the position vector, we would have rho dot n rho plus rho n rho dot plus z dot and z. We should be able, right, to calculate what is rho dot, what is phi dot, or maybe rather n rho dot and phi dot by, actually this should be phi dot and phi, while this should be minus phi dot and rho. And within this substitutions, we could then find both the velocity, which I will not maybe completely write down, and acceleration by substituting this for this, and furthermore applying one more derivation. Then we have also considered this review I'm doing especially for the second group, which didn't participate in the kinematics considerations for the Polish-speaking group. We also considered normal reference frame with a following consideration, that this is the way to describe motion within the reference frame, which is sliding on the trajectory. So we would have three mutually perpendicular axes, but they would be defined in such a way that the n tau versor would be parallel to velocity. So the velocity vector, which is always parallel to trajectory, if we have a trajectory here, here we would have a tangent velocity vector, which is in every point tangent to the trajectory. So v and tau was defined in that way, which led us to defining n tau as v over magnitude of v, and then we would have to find another versor which would be perpendicular to n tau, so that we need to have always three mutually. This is a Cartesian reference frame. This one is cylindrical reference frame. Anyway, what is important here, that each of them are, from this set of versors, each are mutually orthonormal, geometrically perpendicular, so that normally you can use them in linear combinations to define any vectors from R3, because what we are referring here is three-dimensional space of real numbers, but you cannot define any of them using the remaining ones. This is linear independence. You probably had discussed this within the framework of algebra and linear spaces. So in order to describe a proper reference frame, like this cylindrical example, Cartesian reference frame, normal reference frame, we need to have three properly defined mutually orthonormal, so normalized and orthogonal, meaning perpendicular in terms of geometry, versors because these are vectors normalized, so the term is versor. And in order to find one here in such a consideration, one can show that a perpendicular vector would be actually the derivation upon time of this vector of n tau to define nn. So how to show it? That scalar product of normalized vectors by itself must be equal to 1, and you can apply the derivative operator on both sides. So this means that you have dn tau over dt in scalar product with n tau, but then you need to take first function and the operator of the derivation for the second function. But scalar multiplication is commutable. It's commuting, so you can change the order, and then we will have two such terms, and the constant is 0. So 2 is cancelled anyway, and that means that dn tau over dt is really perpendicular to in tau because the scalar product is 0. So if that is the case, you can use maybe define an n-versor as dn tau over dt and normalize it by its magnitude. So that is now a normalized vector. Okay, and finally, the convention requires third versor, which we can refer to as the binormal, and the binormal versor must be perpendicular to both nn and perpendicular to n tau. So the binormal versor can be achieved, can be defined by using the vector product operation. So there would be n tau in the vector product with nn. And then you have 3 mutually orthogonal versors. Now, with this being a key equation for velocity and leading to the acceleration in the following way, that acceleration is therefore velocity dot, the first derivative of the velocity. So this is v dot n tau plus v, because here this function is time dependent. It will change with the trajectory, since here, for example, it would point like this. So it's always tangent to the trajectory. That's situation for time dependence quite critical here. Time dependent. These are not time dependent, and among these all are time dependent. So they are sliding together, as I mentioned, with the trajectory. Okay, this is time function, and maybe time function here as well. Right, and when we have multiplication of 2 time functions, like in that case, this is a scalar velocity and this is a versor of n tau, then you need to take derivation of the first function multiplied by the second function plus first function multiplied by the derivation of the second function. So in that way. So acceleration is such term, but this can be exchanged with nn multiplied by dn tau over dt in terms of magnitude. So you can change this into the following term, that you have v dot n tau plus, and here you have velocity value multiplied by dn tau over dt and multiplied by nn. And that is a tangent component of acceleration, and that is normal component of acceleration, tangent and normal in the normal reference frame. And this one can be also substituted to v square over r nn, meaning that you introduce actually something that would be called the instantaneous curvature of trajectory. And this instantaneous curvature of trajectory r must be equal to what? It must be equal, so that, let's check it in the following way, v square over r must be equal to v dn tau over dt. So that means that r is equal to, here this would cancel, so r is equal to actually v divided by dn tau over dt. Okay, this is how the normal component will look. And you can apply these different reference frames for description of different types of motions which are sharing symmetries, similar symmetries that the reference frames define, because it is maybe quite complicated to introduce these equations, to calculate them, especially with calculating these derivations. However, when you would consider a complex symmetry motion, such as, for example, motion over a circle or maybe motion over a spiral trajectory in standard Cartesian reference frame, where in Cartesian reference frame you have this one, and within such an approach, the position vector is a linear combination. Here is just an alternate way of denoting this one. It's x and x plus y and y plus z and z. And then the first order derivative is velocity, and that is equal to x dot nx plus y dot and y plus z dot and z. And that is quite convenient because these versors in the Cartesian reference frames do not depend on time. They are not varying in time because the Cartesian reference frame is stationary. When you have your motion in the Cartesian reference frame, this remains the same within the definition of the versor spanning the reference frame. Here are these versors. This is nx, ny, and z, and they are not changing, not varying in time. While whereas in this, for example, cylindrical reference frame, you can see that they will be moving, changing the direction, because if the point travel, for example, here, then this versor n rho, this is n rho versor, here should be n rho, this is n rho, this is n phi, this is nz. And the versor n rho would point in opposite direction, right? And here maybe would point, or whenever. It's always on the prolongation of the radius of the cylinder, while the point is always trapped on the verge of the upper wall of the cylinder. So here the situation is, as you can see, that this versor spanning the reference frame change in time, and that makes complicated calculations for velocity and acceleration, where velocity is the measure of how fast the position changes, while acceleration is the measure of how fast the velocity changes in terms of operator of derivation, because the derivation is mathematically defined as the increase of the function due to infinitely small increase of the argument normalized by the increase of the argument. So basically, it tells you how fast the function grows in infinitely small increase of the argument. And this has physical interpretation for the velocity in motion. For example, when you are considering three-dimensional space, which corresponds to our real classical space in our reality, that we can consider motion in, then the motion consideration is first the position, but then how fast, what is the rate of the position change, how fast the position changes. That's the velocity, and that is mathematically corresponding to the derivation. While second derivation of position, or the first derivation of velocity, is the function measuring on how fast the velocity increases. So that is acceleration. And the acceleration is also simple in the Cartesian reference frame, but not so for complicated motions. Because if you have, for example, even very simple circular motion, regular circular motion, and you want to consider it in Cartesian reference frame, then the obstacle you're facing is that you need to somehow bind together dependence between x and y on a constant of motion, which is radius, right? When you have a circular motion, this is a position vector, and we limit our consideration to just 2 dimensions, for example. That's a y, x, and this is r. Then your x is equal, or maybe r, in terms of magnitude, is equal to the square root of x squared plus y squared. And it's constant because that's the radius. So maybe let me write this capital letter radius. It's the radius of the circle upon which this motion takes place, and that is equal due to Pythagorean theorem to this, right? Because r squared is always equal to x squared plus y squared if you consider this kind of triangle. That's x, that's y coordinate, and this plus this squares, square of that plus square of that is equal to the square of that. Right. So the problem is that if you define, for example, y as from that, it will follow the square root of r squared minus x squared. Then if you put it here for example, velocity, you need to calculate the derivative of such a complex function, which has an external function square root, an internal function x squared, which is a time function. X is function of t. So when you derive upon t, you need to calculate complex function with internal dependency, and then you get something even more complex, like square root in the denominator, right? And then you would need to calculate for acceleration a second derivation of square root in the denominator. So it's even more complicated, and pretty fast grows to probably very complicated equations, which would take us a long time to even write down. And that is the reason why you resort to different reference frames, like, for example, a cylindrical reference frame in which such consideration is very simple. All right, so that is basically kinematics. Kinematics deals with formal description of motion using such physical quantities as position and then velocity, the rate of how fast position changes, and then acceleration, the rate of how fast velocity changes. You can, of course, build up on this chain indefinitely because you can define another derivation of acceleration, how fast acceleration changes, and this is called a jerk. And then you can move on further with subsequent derivations that do not even have a name on their own, but maybe they are not very common and not very practical to use. So generally, kinematics is limited to only the first derivative and the second derivative of the position vector. That means velocity and acceleration. Jerk is rarely considered. And pretty much that's all in kinematics. So kinematics can be considered mainly as some terms in terms of geometry, applied geometry, which generally doesn't do any physics like answering the questions about nature and so on. It's a formalization of the description of motion. Right, and the chapter that deals with the cause of motion is the second point today, dynamics, which we'll move on to. Dynamics is about the cause of motion, as I mentioned. What causes the motion is the main question for dynamics. And in order to answer this question, well, this consideration, of course, can be done in many different levels. And maybe the most general level that we know, based on some space-time symmetries and associated with another theorem, is generally something that we refer to as Hamilton's principle. And this Hamilton's principle states that physical systems generally evolve in such a way as to minimize their energy. In pretty much kind of a simplification, and more precisely, you would say that to minimize is action, and action is somewhat related to energy, generally very close, with action being subtraction of the potential and kinetic energy, and energy being mechanical energy being an addition of kinetic and potential energy. We'll be dealing with that energies in more detail later on. But within this consideration, you can generally understand it as energy and say that systems will evolve in such a way, evolve meaning will change their physical quantities. For moving system, they will simply mean that it will move along the trajectories in such a way that to minimize this energy. And that is maybe the most general principle that we know in physics, especially in classical physics, which can be then, of course, formulated alternatively in some more specific approaches. And one of these approaches is Newtonian physics. As a matter of fact, it happens that the Newtonian laws of dynamics that you probably well know from secondary education, like, for example, the basic motion equation that force is equal to mass multiplied by the acceleration. That is basically the answer for this question. What causes the motion is the force. That is actually, these laws of Newtonian dynamics are solutions, maybe special solutions of this more general principle that we refer to Hamilton's principle. Okay, so this is quite important, and this has also very general background associated with quantum mechanics, because we consider now some very basic traditional classical physics that is later on in maybe beginning of 20th century has been gradually replaced by contemporary physics that can be divided into relativistic physics, which is still the domain of classical physics, and quantum mechanics, which is something very different from classical physics. And then quantum mechanics corresponds, maybe partially overlaps with the topic of consideration of dynamics in general, because dynamics plus kinematics together, they make mechanics. So we have classical mechanics, and most general formulation of analytical classical mechanics is this Hamilton's principle. So you could say here maybe Hamilton's principle. right? And this is something which is common also for quantum mechanics and classical physics. And here we consider classical dynamics as part of classical mechanics. And then there is this more special formulation, or perhaps a solution also for Hamilton's principle, which is called Newtonian physics. That's one of possible, or Newtonian dynamics. That's one of possible consideration of dynamics. So we will refer to this one, to the Newtonian dynamics, and we'll discuss it in more details, because to introduce in detail Hamiltonian's principle and the consideration of analytical mechanics, that would take us too much of time, and that would generally be considered out of the scope of some basic physics approach. So it's a little bit more advanced consideration. So we limit ourselves to something traditional that you already know, but we will do it maybe in some fresh approach, with first defining very important aspect of inertiality. So for Newtonian dynamics, generally what's important there are laws of dynamics, laws of Newton dynamics. And within these laws, the first one is that there exists the inertial reference frame. And all right, within this notion of inertiality, what do we understand by this? Inertiality is, simply speaking, acceleration of the reference frame. So if you have a reference frame which undergoes acceleration, then this is non-inertial reference frame. While if there is a reference frame which does not accelerate, acceleration is 0, then this is inertial reference frame. This is perhaps a very crucial notion for the whole idea of classical dynamics, but also quite simple. You can understand that whenever you consider maybe some systems that are accelerating, then within the systems, what you would observe that some observers within systems that accelerate, let's imagine maybe an elevator, so something more like this. There is a person standing inside of the elevator. The elevator starts to accelerate, being pulled by its rope, right, by its mechanism to lift the elevator up. Then what will happen is that this reference frame starts to escape from under the foot of this person inside, from the observer. And from his perspective, he will be pushed by a force which will push him towards the floor. And this force is called inertial force. This is actually some kind of special inertial force called the D'Alembert force. This is exactly the linear opposite direction, which is equal to the mass of the person multiplied by the acceleration of this reference frame, departing from inertiality. When the reference frame is stationary, not moving, then there is no force acting inside of it, right? It's a similar case with the bus, for example, that stays just on the bus stop and does not move. But whenever the bus starts to accelerate, then people inside will feel acceleration, or maybe a force, we should say, pushing them in the opposite direction of the acceleration of the bus. Simply speaking, from the person outside looking on the situation, it will be obvious that it's not any force of material origin, but just this reference frame, the bus, going under the feet of these people inside of it, right? And simply it's moving, and they are not moving. So from their perspective, they perceive that they are being pushed against the back wall of the bus. Similarly, maybe in a car, when there is when the car goes high velocity and starts to brake, then passengers and the driver are being pushed against the front screen, right? Because now the acceleration is oppositely directed. So they had some velocity, and now the car stops. So it would be like, again, the reference frame getting away under them in the opposite direction. So inertiality is very crucial concept here, because maybe in traditional formulation of Newtonian dynamics that you remember from school, is the first law of Newton's tells us that whenever we consider an object which is not being acted upon by any force, then it will move with a constant velocity, and in particular, if this constant velocity was equal to 0, then it will remain at rest, not moving at all. But here, what really that means is that if there are no forces, then these objects will not change their direction of velocity because there will be no force that could cause it. And one important thing that you should add this is that the first law of Newton's dynamics, as a matter of fact, like the remaining two, all of the three Newton's dynamics laws, are only considered for inertial reference frame. So to be more precise, you should say that in an inertial reference frame, the object moving with constant velocity and not being acted upon by any external force will remain moving in constant velocity, in particular staying at rest if this constant velocity was 0. So maybe easier way to formulate it is simply to say that there exists inertial reference frame, and to define what is the inertial reference frame is, just as we've done, that this is inertial reference frame is whenever the reference frame is not undergoing any acceleration, right? And there is, however, a big problem with this consideration of inertiality, because different reference frames have be identified as such. And can we really find physical inertial reference frames? And this is to some extent problematic, because when we say, for example, Earth surface could be a candidate for inertial reference frame, we can verify it negatively quite easily with some basic experiment, which is called focal point pendulum. When we set in motion a pendulum on a long string, then we will notice that after some few minutes, the plane of the oscillation of this pendulum will shift slightly, will rotate by a certain angle. This is, of course, because of the fact that the Earth rotates around its axis. So what really will happen that under this pendulum, the Earth's surface will slightly rotate through some minutes of its motion, of this pendulum motion. So, but from the perspective of this reference frame, which is when we fix our reference frame to the surface of Earth, of course, in this reference frame, the Earth will not be rotating because this reference frame is fixed with Earth. So it will rotate with Earth altogether, so it won't be possible to notice this rotation. But since there is an acceleration, there will be an inertial reference frame, an inertial force that will deviate a little bit this plane of the focal pendulum motion, right? This is how you should consider it. So the problem of finding really a physical reference frame which would be inertial is probably not very obvious, and even we cannot say at this stage if there exists such a reference frame which would be truly inertial in our universe. So because, for example, one can say, let's define maybe if not Earth, if Earth is not a good candidate, what about Sun? Of course, the Sun is also in motion. It rotates around its own axis, but also it actually orbits some region of space. To be more precise, the center of our galaxy, because solar system is one of the stars of the Milky Way, in the arms of Milky Way, which of course rotate around its own center point, which is located in the Sagittarius A, supermassive black hole. And also, the center of our galaxy is not a good inertial reference frame because the galaxy itself orbits some larger structure of matter, some local groups of galaxies which have some local center of the gravity which is being orbited, and so on. And all structures in the universe are in motion. So in rotational types of motion to further add to that, which means that always with rotations there are non-zero accelerations associated. And therefore, physically, indeed, you can question quite significantly this first law of Newtonian dynamics, that really maybe there is a problem with the statement that there exists inertial reference frame. Okay, so the consequence of that is, okay, what can we do about it? And it turns out not so bad, because even if reference frames are not inertial, meaning that they accelerate, we can easily correct these equations by introducing these inertial forces. They are non-material in origin, but simply speaking, they are kinematic corrections to the equations. Now, we'll be able to derive step by step, which we'll do maybe in some subsequent lectures, step by step, all corrections, kinematic corrections to the departure of the reference frames from inertiality. So this is what we'll be doing. Now, maybe most central law of Newtonian dynamics is the motion equation. Motion equation, which states that force is equal to mass multiplied by acceleration, and that is mass multiplied by the second order derivative of the position upon dt squared. Okay, so this is the equation, which really is describing everything in classical physics, and this may be traditional classical physics in terms of its Newtonian formulation. So everything really is resolving around this equation, which has a very important property because, as you can see, it is a second-order derivative equation due to this here second-order derivative on the position vector. And mathematically speaking, there is an important theory in the consideration of differential equations. So it's some advanced analysis that maybe some of you will have an occasion to learn during your course of the program of studies. Nevertheless, the consequence of this theorem is that there exists only one unique solution of this kind of an equation. So second-order differential equation has only one unique solution. So there is a theorem about uniqueness of solution of the second-order differential equation. And this unique solution really means that there is determinism, because initial conditions, along with the equations, will give us a unique solution to it in arbitrary future. So that means that any future is always determined by the past, and vice versa. The future also determines the past. Right, so this is very important. In classical dynamics, we have something which is referred to as determinism. And that is also the case for relativistic physics, where we'll introduce relativity due to Einstein, and this relativistic physics changes the notion of time consideration in actually consideration of classical physics, in classical mechanics, because the time is treated just as a parameter of varying different physical quantities in standard approach, in traditional approach, while to explain a very important and maybe quite puzzling also observation that the velocity of light is constant and does not depend on the reference frame in which you measure it. In other words, anyone moving with any arbitrary velocity will measure a ray beam, the same ray beam of light, to propagate at exactly the same value of speed. So the speed of light is c equal to 3 multiplied by 10 to 8 meters per second, so 300,000 kilometers per second. It's pretty huge velocity, but still limited, finite, and constant. No matter how fast you move, you'll always observe the same velocity of light. And the consequence, to logically explain this peculiar fact, this peculiar empirical property of nature, is that the time will flow differentially depending on the velocity with which you move. So that, for example, a person hypothetically moving in a spaceship that attains velocity of maybe close to the velocity of light, his time will slow down indefinitely, up even to infinity, and then the time outside for him will flow infinitely fast. So in any second that passes for him inside of the spaceship, maybe billions of years will pass outside. That is relativity. And also within the consideration of relativistic physics, within something that is referred to as Putnam-Penrose-Rijkswijk argument, you can also talk about full and complete determinism due to the fact that for each observer that is considering certain event that will be in his future, there always exists another reference frame for which also in the same consistent universe, in the same consistent reality, there exists another reference frame moving with certain velocity, not even big, for which this event in the future of this former observer is already in the past of this reference frame. So that since it is in the past, it already take place, and that means that it's determined in the future for this former observer. That is an argumentation for a complete determinism in classical physics. So there is no place at all for any concept of a free will, for example, if you will, for consideration of consciousness and so on. But quantum mechanics introduces non-determinism, so maybe there is some place for such issues. In classical physics, everything is determined, and in standard consideration of non-relativistic dynamics, this is due to this second-order differential equation and its uniqueness property, unique solution theorem, which corresponds to this idea of the determinism. Okay, and what else? There is also a third law of Newtonian dynamics, which is referred to in simplicity action-reaction principle. Action-reaction principle, which states that every force is reciprocated. So when you have, for example, force of physical system A acting on B, that force will be reciprocated and equal to oppositely directed, but the same up to the value force that the system B will act on the system A. It's like you can hit the wall and the wall will hit you back with the same force as you apply hitting the wall. So when you hit really hard with your fist in the wall will really hit you quite hard, the same magnitude of force, oppositely directed force. And this also refers to quite an important conclusion that forces are of material origin. Except of these kinematic corrections, which really are not true forces, but as mentioned, they are just corrections of kinematic nature to the departure of the reference frame from inertiality condition. Okay, and this is the framework of the dynamics. We now know this is the answer, the cause of motion, to the question of cause of motion. And now maybe it's a good time to consider some examples of certain forces or interactions really existing in nature. Okay, so let me erase maybe the whiteboard again. And the consideration is forces in nature. So we'll start with gravity. Of course, everyone knows it well. This is the force that keeps us on the surface of Earth. Maybe some of us has, to some extent, been able to overcome it. For example, I don't know, by using a plane, passenger plane, which can lift up due to the aerodynamic forces, which will balance down or even overcome the gravity force. Also, the thrust of the jet engine and so on. So, but the gravity normally is quite significant experience of our everyday life, of course, and how it works. Well, it is a force of material origin that we designate here with G, which is equal to the constant G, which is called Einstein gravity constant. Okay, it's about 6, not sure, multiplied by 10 to minus 11. Now about the unit, let us see in a moment, but the full equation is mass of one object, mass of another object, divided by the radius to the power of 3 multiplied by radius vector. So in terms of magnitude of this force, I do not write a vector now, meaning that this is a magnitude of this vector. So more precisely, this is something like this. G. Okay, and that is equal to GMM over R square, because here this vector was magnitude of R, which cancelled with the magnitude to the power 3 in the denominator. So it's the magnitude of the gravity force is inversely proportional to the square of R, to the square of distance between the objects, and linearly proportional to the masses, and also to this gravity constant. Now, the force, because we have force is equal to MA, right? So MA is second order derivative of the position upon time. Then in terms of units, okay, maybe we take it in terms of magnitude, so I don't write here the dash designating a vector. So in terms of units, the unit of force is Newton, and the unit of mass is obviously kilogram, and then we have Here is meter because that's a position, physical quantity, only applied by the differential squared operator. So it's meter divided now by linear differential operator, but on t square. So on the time square, which is second square. So a Newton is kilogram multiplied by meter per second square. While here we would have to, of course, have newtons, but for force, but that would be equal to unknown unit of the gravitational constant multiplied by kilogram square and divided by second square. And we need to get to something like this. So you can see that the gravity constant should be kilogram, should have kilogram in the denominator, right? And meter, maybe, yes, maybe meter in the nominator. Then let me see, this is enough. Yeah, but then it would work out for final consideration to be just kilogram meter per second square, because kilogram would cancel with the square here, and the meter would be multiplying kilogram divided by second square. So no, sorry, here is a big mistake. It's not second square, obviously, here in the denominator, because we have here r square, so it's a meter square. Okay, so it's a meter square, so it changes situation a bit. So it must have meter to the power 3 cube meter, because this would cancel with meter square, and 1 meter would be left in the nominator, and then we should have second square here. Yeah, so this is the unit of the gravity constant. Meter square divided by kilogram multiplied by second square. Something along these lines, probably. Okay, so what about this gravity magnitude? If we say, okay, what is the, maybe let's first start with the gravity acting on us, on an average person on the ground, right? So the mass of Earth is pretty huge. It's about some 10 multiplied to the power of 22 or something like this. So in kilograms, it's pretty huge value. The mass of a person, let's assume for the simplicity of calculation that it's 100 kilograms. Okay, and then this person standing on the ground will be under the action of something that we refer to as weight. And what is this weight? This is the force of mass of the person and the acceleration acting on him. But what is the acceleration? So let us see again the gravity force. Maybe here it's written, right? But on the same hand, I can write that the gravity force is mg, right? Because normally I should write ma on the basis of this equation from second law of Newtonian physics. So ma, but this is some special acceleration, which we refer to as Earth acceleration, Earth gravity acceleration, and we call it small g. And this small g, when I compare this equation, this one with this one, because that's the same, I can see that this small g must be equal to gm over r square. However, this is for Earth, so this should be r square, where this capital R is the square of Earth. Okay, what is the square of Earth? It's about 6,000, maybe 400 kilometers, something like this. So you take mass of Earth, you divide it by the radius of Earth squared, you multiply it by the gravity constant, and you get your acceleration g, which we know quite well what it is. It is in approximation 9.81 meter per second square, which can be further approximated to about 10 meter per second square. So when we consider the force acting on a person who has a mass of 100 kilograms, that would be mass multiplied by acceleration, to be precise. But this acceleration for Earth, so that is weight, is the force of the gravity of Earth, is defined by the acceleration of Earth. So it's a small g. So eventually it's 100 kilograms multiplied by 10 meters per second square. Okay, what else can we say about this unit of g? Or, as a matter of fact, for any acceleration, here, if we look at this equation, a is equal to f over m. So the unit for acceleration is also Newton per kilogram. So you can say that this is meters per second square, but also newtons per kilogram. That's actually the same. So you will have 100 kilograms, right, multiplied by meters per second square, right, which really gives us Newton. But if I would have here Newton per kilogram, the kilogram will cancel, and I would have also a Newton. So it's a Newton anyway. So it's about 1,000, right? This is equal to 1,000 newtons. That's the force of gravity acting on maybe a little bit over average adult person who weighs 100 kilograms. 1,000 newtons, so 1 kilonewton. It's pretty much force, because if you try to lift 100 kilograms, some kind of an object which weighs 100 kilograms, it will be pretty heavy. You should be putting a lot of effort to weight up 100 kilograms, even if possible, right? This is a quite large force applied. Now, what about different manifestations of gravity? Now, let's assume that we are interested on the force that the gravitationally will affect 1 kilogram of matter with 1 kilogram of matter at 1 meter. Here, when we define the gravity force, to be more precise, you should say that this is minus here because when you have your reference frame and you have your one mass here, okay, and you have another mass maybe here, you have a position vector here, then the force will be in attractive nature. So the gravity force here will be oppositely directed to the position vector. The position vector points like this, while the gravity force points oppositely. So if you measure it in terms of the position vector, it's negative. It's oppositely directed to the position vector, and always, right, it's this force we call central force in terms of its vector, because it will always be directed parallelly to the position vector. So it has a spherical symmetry, or a central force. And now, so it's universally attractive force. Whenever you have matter, the matter will always attract with another matter, with another material object, and proportionally to the mass of these objects. And when you have 1 kilogram and another kilogram of mass, then, of course, this one will be pulling this one, so it will be Fg, and due to the action-reaction principle, this gravitational pull will be returned, reciprocated, as we say formally. As a matter of fact, for Earth, the same situation goes. The person stands here, and the Earth is pulling him down gravitationally with Q, but the person is also pulling Earth with the same magnitude of 1,000 newtons towards himself. Right? That's a situation we deal with here, but actually, 1,000 newtons pull for Earth is completely unnoticeable because of the huge mass of Earth. So we wouldn't really see Earth falling on us, but it's again a matter of convention how we want to define the reference frame. So, okay. Now, what about this force on pull of 1 kilogram against 1 kilogram at 1 meter? So for this situation, the gravity is G, 1 multiplied by 1 over 1, so it's just G. So when we substitute, it's about 6.62 multiplied 6.62, I believe, multiplied by 10 minus 11 newtons. Now, 10 minus 11 newtons is really small because it's like you divide by the number which has 11 zeros. So it's really very, very small number. So you can say that completely irrelevant is the magnitude of the force at which, for example, a kilogram of sugar is attracting another kilogram of sugar. It's negligible. You wouldn't even be able to measure it using some normal mechanical devices. You would have to use some very precise, maybe laser interferometers to measure such accelerations that would be due to the force of such small magnitude. Okay, so gravity is very small, But of course, when you consider macroscopic scale of the universe around us, it starts to be pretty relevant, pretty important, and actually dominating force in the large-scale universe because of the huge mass concentrations and huge masses of stellar objects such as stars, galaxies, solar systems, and planets, and so on, and especially black holes, which are supermassive objects, which we'll deal with later on in terms of matter corresponding to the curvature of spacetime, and this curvature being completely closed for black holes. Okay, so this is gravity. Okay, maybe we'll come back later on to revisit gravity in terms of maybe some consideration of the relative magnitude of gravity against electromagnetic forces, because the second one interaction that we'll be considering is electromagnetic interaction. So electromagnetic forces can be divided into electric, as the name points, and magnetic. So generally, this is field of electrodynamics, this field that I wanted to discuss at the beginning of the lecture, but it is probably shifted on to some further lectures. Right, this was my mistake. We are doing here consideration from the beginning of general physics. So here we'll just very briefly refer to what we have in because in details in electrodynamics we consider two fields, electric and magnetic fields, which are vector fields, and they correspond actually to the vector mathematical concept of a vector field, which assigns vectors to different points in space. What these fields do are they are just a way to describe forces that are electric and magnetic forces, and they are coupled together within the framework of four mutually coupled equations, some linearly combined equation system that we refer to as Maxwell equations. And this Maxwell equation tells us about some topological features of those two fields and how they depend on each other, one on each other. For example, electric field is generated by magnetic field in terms of wheels, so that maybe vortexes. The vortexes of the electric field are generated by varying in time magnetic field, while electric field itself has sources as well, which are generated by charges. So charges are sources of the lines of the electric field. While for magnetic field, the situation is different. Magnetic field has no sources because its divergence or multiplication with the gradient is scalar product with the gradient is zero. And it only is generated by varying in time electric field in terms of vortices, but also by moving charges with certain velocities. Okay, so briefly, I will sketch you a Maxwell equation so you can have a look at them. Of course, this is maybe a little bit too early, but I will not in detail explain them, maybe just very shortly. Divergence of electric field, rotation of electric field, it's dB over dt. Then divergence of magnetic field is zero, and the rotation of the magnetic field is j vector over c square epsilon zero, the electric permittivity of void, plus 1 over c square, and here maybe minus dE over dt. While rotation of vector field A is gradient in vector product with A, and the divergence of vector field A is gradient in scalar product with A, and the gradient is a vector of a partial derivatives, which really is a translator operator in space. So if you want to translate some by certain vector, then this gradient is the operation you use to translate this vector. And the divergence is the scalar product with the gradient operator. This is topological feature of a source or drain. source or negative source, which we refer to as drain. And a rotation, on the other hand, is a vortex. So these equations really tells us about topological structure of these fields, electric and magnetic fields, that the sources of electric field are charges, where rho is the density of charges, volumetric density of charges, which is derivative of charge upon volume, while J is density of charges multiplied by the velocity. So this is a flow of charges. Okay, and this corresponds to sources, as you can see, of electric field, and this corresponds to the vortices of magnetic field, because rotation is here present with this we call charge density, and this we call current density. So charges, density of charges flowing with velocity, the current density. And magnetic field is generated in terms of vortexes with moving charges, while also vortexes of electric and magnetic field are generated by changing in time corresponding field. For electric field, changing in time magnetic field. For magnetic field, changing in time electric field generates vortexes. Okay, and for interactions, we deal with Lorentz force. Lorentz force, which is FL equal to charge multiplied by the electric field plus charge multiplied by the velocity in the vector product with the magnetic field. This is in general, right? But maybe to simplify it a little bit, we use Coulomb interaction, Coulomb force. And the Coulomb force is just this one, but also for a spherical distribution of charges, some homogeneous spherical symmetry, which refers to, or maybe single charge as well, because also it contains, it conveys this property of spherical symmetry. Then it resolves pretty simply to something like this, that the Coulomb force Fc is equal to 1 over 4 pi epsilon 0, where again epsilon 0 is, you see this here present, it's a permittivity of void, the electric permittivity of void. It corresponds, it's important, it's an important physical constant which corresponds to electromagnetic field propagation in void. Actually, when you solve these equations for the assumption that there are no charges present in space, so generally rho and J are 0, you can see that this is 0 then, this is 0 here, and these two equations are becoming for electric and magnetic field very similar. Like only what's left is rho E, rotation of electric field is minus dB over dt, and rotation of magnetic field is 1 over c squared dE over dt. So very, very symmetrical type of equation, and these types of equation lead to something that we call a planar wave equation from Maxwell equation, and the solution of the planar wave equation is the plane wave, planar wave. And this wave is, of course, of electric and magnetic field, we refer to as electromagnetic wave. And from this constant present here within the Maxwell equations, 1 over c squared, we can find formally that this wave, electromagnetic wave, propagates in void with the velocity equal to c, right? And the constant governing this propagation is this epsilon 0, the electric permittivity constant. And what's important here is that since Maxwell equations will hold in all inertial reference frame, of course, inertial reference frame can differ with their velocities, just under the assumption that they do not accelerate, but may have different velocities. And always in every reference frame differing with velocity, Maxwell equation solutions will be the same, meaning that the propagation of the electromagnetic wave will happen with the c velocity. And that is the interpretation of what really light is, that light is the electromagnetic wave propagation. Light itself is electromagnetic wave. Right, and for the Coulomb force, we get very similar to the gravity with the QQ over r to the power 3 multiplied by the position vector r, where in terms of the magnitude, okay, maybe this is not needed anymore. In terms of the magnitude, these is quite similarly as for gravity, 1 over 4 pi epsilon 0 QQ over R square. So again, central symmetry, so it is a central type of force. What's different here is this not universally attractive, because Q can be of either sign. Like mass can be only positive, charges can be negative as well, and the elementary charge is the charge of the electron, negative, is minus 1.6 multiplied by 10 to minus 19, okay, coulombs. And the positive charge is like the charge, elementary positive charge is like the charge of the proton, is 1.6 positive multiplied by 10 to minus 19 C. Okay, so eventually you can have these charges both negative and positive, and from the equation it will follow that if you have different signs of charges, there will be a minus, which will similarly as for the gravity, which will mean that they will attract, so that the force will act parallelly to R but in opposite directions. So it will attract two elementary particles like an electron with for example a proton. They will want to get together. But if you have two protons or two electrons, they will repulse each other, because then the sign will be positive. For example, two electrons will have two minus signs, which will cancel out, and will be a positive force acting in the same direction as the position vector from one to another. So they will be repulsing each other. So electrons doesn't want to get close because of the electromagnetic, or actually here electrostatic. We consider Coulomb force as an electrostatic force, because charges do not need to move for this force to exist. So it's electrostatic force. Okay, and now what about its magnitude? Now let's assume that we consider maybe 1 Coulomb with 1 Coulomb over a course of 1 meter. So now this epsilon 0 is somewhere on the order, so that this full constant 4 pi is about 12 or maybe more, 14, something like this, because pi is 3.14. Okay, so maybe it's something around in more than 12. Okay, and to the power of 10 to minus 9 for the epsilon 0. But since epsilon 0 is in the denominator, eventually this constant will be around 10 to 9. So it's pretty significant large. And Coulomb multiplied by 1 Coulomb will be obviously 1 over 1 meter. So we will have also 1. So the Coulomb force will be about up to the magnitude about 10 to 9 newtons. Okay, because here, what would be we want to have newtons, and here we have, what do we have? We have Coulomb multiplied by Coulomb over meter square. So Coulomb square over meter square, right? And what do we need to get the Newton? We need to have, Newton is here. A kilogram meter per second square. So this must be second square in the denominator, okay, kilogram in the numerator, meter to the power 3 in the numerator, and Coulomb square in the denominator. That would be the unit of the dielectric permittivity constant, okay, something like this. Now, what you can see is that the force is 10 to 9 newtons, so it's a pretty huge force. It's like 10 to 9 newtons is maybe how much? Billions, 10 billions newtons, right? So when you look at this, it's like 1 million of people, each of mass of 100 kilograms, so weighting 1,000 of newtons. When they stand together, the combined weight of 1 million of people will be the force of 1 Coulomb acting on 1 Coulomb over a distance of 1 meter. So, for example, if you put them on a platform and you use electrostatic force of 1 Coulomb on this platform, and you have another opposite, the same sign of charge accumulated in the surface under this platform, then this platform will hold 1 million people standing on it. just with 1 coulomb of charge. So you can see how huge is electromagnetic force in comparison to a gravity force. So altogether, for 1 kilogram compared against 1 coulomb, the difference is 1 kilogram we have here, so it is 6.62 multiplied by 10 to minus 11 newtons, right? It was so the difference is 20 orders, not 20 times, but 20 orders. So it's gravitational force is in comparison to the magnitude of electrostatic force, like divided by 1 with 20 zeros, such a number, huge. So completely incomparable. But this is even not correctly pronounced, because it's pretty arbitrary to say, to compare kilogram against the coulomb. We don't know how to relate kilogram to coulomb. So much better approach is to compare maybe elementary particles' masses against their elementary charges. So if you do that, so please think about maybe an electron. Okay, maybe the mass of electron is not sure, but let's assume that it is 10 to minus 24 kilogram. It could be much smaller. It could be maybe minus 28 as well. I'm not sure right now, but let's assume that it's even. Maybe I'll check. Just give me a second. Electron mass. No, it's even smaller. It's 10 to minus 30. So not at all 10 to minus 24. It's 10 to minus 30 kilograms. And more precisely, it's 9 multiplied by 10 to minus 31, but 9 is close to 10, so we can say it's 10 to minus 30 kilograms. And the elementary charge is here, like minus 19. And we want to know the force that 2 electrons will repulse each other at a distance of 1 meter. So what the force will be that. So first, the Coulomb force is 10 to 9 in approximation. This is this constant 1 over 4 pi epsilon 0, the dielectric permittivity of void, multiplied by 1.6 we omit, so it's just 10 to minus 19 squared. So 10 to minus 19 is like 38. 10 to minus 38, right? And we divide by 1. Let's do such consideration. So yeah, seemingly that's the case. So the result seems to be 10 to minus 29. That's the force that an electron repulses another electron at the distance of 1 meter. Of course, electrons are much closer when we consider the model of an atom. Then we really consider electrons orbiting protons, which are constituents of the nucleus of an atom. They are together with neutrons, or unless you consider some light particle, light elements like maybe hydrogen, and there are no neutrons, just single proton is making a nucleus. And this nucleus is being surrounded by actually delocalized cloud of the density of probability of finding electrons. So we call them orbitals, and this is, to be more precisely, the domain of quantum mechanics, where the trajectory loses its notion. There is no particle anymore. The particle dissolves around space, more likely to say. And different interpretations mean that the particle really is in many places simultaneously, or depending on the interpretation, it could be parallel universes maybe, and so on. Nevertheless, for the consideration of the scales where we have these interactions between particles, elementary particles, these scales are somewhere around nanometer scale. So 10 to minus 9 meter, or even smaller, 1 angstrom, it's 1/10 of nanometer, so 10 to minus 10 meter. So such is the scale. Now, what about gravity? The gravity, if we compare at the same distance, because we wanted to compare forces of electrical interaction, electrostatic interaction, Coulomb interaction between electrons, and the gravity between electrons on the same comparison ground, so on the same distance of 1 meter, this would be 10 to minus 11 right, multiplied by masses of two electrons, which would be 10 to minus 60, right, because it's 10 to minus 30 multiplied by 10 to minus 30 for the masses, and divided by 1. So altogether, it's 10 to minus 70 newtons. So what's the real difference between these two? You can see 10 to 31, not even greater, 41. So the difference is that Fg is smaller. The gravity force is smaller than the electricity force, the electrostatic force, Coulomb force, by 41 orders, by 10 to 41 times. So 10 to 41 times means 41 orders. So really huge difference. So you can see that for matter structures and so on, where they are governed by electromagnetic interactions, gravity is pretty irrelevant. It doesn't compare completely to the magnitude of the force of electricity. Therefore, it is not present there. Of course, it is present, but completely can be neglected completely because of its small, incomparably small value in relation to other forces. So you could say that in terms of matter structures and actually everyday experience that we have with any physical objects, with, for example, the situation that you hit the wall with your fist and the fist does not go through the wall, but is stopped by the wall, or the same that you can, for example, I don't know, maybe pour some tea into a glass and everything is set in place, is due to electric and magnetic forces. We only deal with gravity with the notion of weight. Of course, it's quite a broad experience of our everyday life, but all physics of interactions with matter is due to the channel of electromagnetic interactions, mainly electrostatic forces. Even all chemistry, a constitution of molecules from physical elements, are due to electric forces, electromagnetic forces. How? Because of the structures of electrons, how they really fill up the orbitals, the quantum levels in the orbits around nucleus of atom. So this is because of the fact that there is some principle that we call Pauli exclusion principle, that electrons cannot reside in the same quantum state. So they have a proper quantum number, which is referred to as the spin. It's more or less like a vector of corresponding to a quantum counterpart of angular momentum, which we will also define in subsequent lectures. But the idea is there that due to these electrons filling certain energy gaps, we'll have different configurations of atoms in getting into chemical reactions. So they are bound together with sharing of the electrons between these orbitals. With the orbitals filled by electrons, which is actually the science of chemistry, mostly reduces to that, regulated by the Pauli exclusion principle of how many electrons you can have on certain energy orbitals over atoms. And that makes basis of chemistry. So actually all, for example, reactions that you can maybe exchange mass into energy, produce energy from matter, in terms of standard chemistry, all fuels that are burned, like, for example, rocket fuels, or maybe even standard diesel fuels in combustion engines, such as also jet engines, rocket engines. It's all the electromagnetic forces in play. So they are not very powerful. What you can get from them is you can, of course, lift some objects even on the orbit by overcoming gravity and set them in motion to high velocity with accelerations driven through rocket engines by combusting chemically active, very exothermic reactions, chemical reactions. It's actually fast oxygenation of some fuels, such as kerosene, maybe with a lot of oxygen. When they are mixed, they are very easily combustible, and a lot of hot gases are created, which are by a certain shape of nozzles, which are pushed away from the engine. And in terms of the momentum conservation principle, the rocket is being pushed in the opposite direction. So that's how the rocket engines work. And the energy you can get is quite a lot, of course, but you need to have a lot of fuel in the rocket. So majority of the mass of the rocket will be the fuel needed to produce enough of thrust to lift some small object like a satellite into the orbit. But there are also other interactions, such as we have here a little bit of space, so maybe I'll use it here, weak and strong interactions, which are even many orders stronger than the gravity and electromagnetic forces, but are of kind of quantum nature. They are beyond of classical consideration of physics. So maybe I will just limit myself, especially as that we are closing to finishing of this lecture, because we do not have a break in the middle, so we'll finish in 5 minutes from now. The weak and strong interaction, the first one is repulsive, the strong one is attractive. However, the idea is that there are many orders greater than electric and gravitational interactions. Like you see, the electromagnetic interaction is hugely greater than gravity by 40 orders. Weak is by many orders greater than electric, but is on a short scale active. It's a short-ranged interaction, short-range force, meaning that it will come into play only on very small distances, like say 1 nanometer, for example. Whereas electromagnetic fields is long range, you can have also, as we just calculated, on a distance of 1 meter even, or greater. Similarly, as gravity can be in an indefinite magnitudes of distances. Of course, it will diminish, but it will diminish pretty slowly, polynomially, with the square of the distance in the denominator. Now, the weak interaction will, as I mentioned, be repulsive in, for example, among two protons that they will be close together. Maybe let's say let's say two protons inside of a nucleus are already bound with a strong interaction, which overcame weak interaction. But before they create together every particle, like helium nucleus, we have a hydrogen nucleus, which is a single proton, and the hydrogen atom can collide with another hydrogen atom with huge energy, overcoming this repulsive interaction that would keep together these two protons away from each other. And actually, this kind of force is the basis of nuclear decomposition, which we also call radioactivity, for heavy particles, such as maybe plutonium, uranium, or some heavy isotopes of some standard particles, where you have unstable nucleus, and it can decompose into lighter particles. This will be a weak repulsive interaction in play. While opposite situation is strong interaction, which is getting objects together and gluing them into heavier elements, nucleus, like helium atom from hydrogen, from two hydrogen atoms. Okay, so this is how it works. And maybe one more thing to say is that this is actually the basis for discovery of the nuclear reactions. And of course, sadly, during the Second World War, this has been developed successfully by United States and even used against Japan in Hiroshima and Nagasaki. Two atomic bombs have been dropped on these cities. These were fission reactions, meaning that they decomposed heavy particles like plutonium, uranium into lighter particles with chain reactions and proper construction of a bomb. That this does not involve single molecules, but it invokes chain reactions of a critical concentration of heavy particle mass, like, for example, this plutonium, and yields a huge amount of energy, with a scale comparable to this magnitude of the weak interaction. That's why atomic bomb is so powerful, because it's many orders stronger interaction than the electromagnetic force that is causing, for example, a traditional explosive. When you measure, for example, you have 1 kilogram of maybe TNT, let's say, or RDX, which is C4, some classical chemical explosive, and they are pretty powerful, of course, but they are limited by the amount of force that you can get from electromagnetism. While atomic bomb, you can have 1 kilogram of fission radioactive material, and it will give you a yield of energy like measured in kilotons or even in megatons. So kilotons are thousands, like 100,000 of tons of TNT, or with megatons, like maybe megatons are not standard atomic bombs. So we'll just comment on this in a moment. Standard atomic bomb may be measured in kilotons, like maybe several dozens of kilotons, means several thousands of tons of TNT. And that is the magnitude of the weak interaction against the electromagnetic force. Right. So the atomic bomb is, of course, huge disaster. In a second, in a moment of time, it killed over 100,000 people in the center of Hiroshima as well as in Nagasaki. Never again, at least, hopefully, the situation will repeat itself. But who knows now with the situation of the war, completely crazy, waged against innocent people in Ukraine. And of course, the history of wars across recent decades, but now this escalation is pretty serious, and who knows what will happen. So it's a complete insanity. Now, something even stronger to weak interaction is the strong interaction. The strong interaction is the force that is now attractive in its nature. So when you overcome the repulsive force of two protons against each other, you can bring them very close on the distance of maybe tens of nanometers, like angstroms. The distance is measured in 1 angstrom, and it is exactly equal to 0.1 nanometer, which is, on the other hand, equal to 10 to minus 10 meters. That's angstrom with this small circle over A, capital A. On this distance, when you are able to overcome the repulsion of weak interaction and put them together, such two protons so very close, then the strong interaction kicks in, and it is able to accelerate on this very short distance these two elementary particles to such a magnitude of energy, kinetic energies, then when they collide, they create, and you have a particle and you have a nucleus from hydrogen element towards the helium element, which helium has two protons inside of a nucleus, but the energy which is generated within this interaction is many orders greater than from the atomic fusion reaction, and it is a synthesis reaction, which is referred to as thermonuclear reaction, or maybe sometimes referred to as a hydrogen bomb, because the material for hydrogen bomb is hydrogen, which over this strong interaction is being synthesized into helium. And this hydrogen bomb or thermonuclear bomb is many orders greater than the atomic bomb. But in order to detonate hydrogen towards thermonuclear synthesis, you need actually to use atomic bomb to compress these hydrogen atoms to such magnitudes that to overcome a weak interaction. Of course, only atomic bomb is able to do it because it's of the magnitude of the weak interaction, because it's based on the weak interaction. So an atomic bomb would be a detonator for a hydrogen bomb, and the yield of hydrogen bomb would be measured in now megatons, in hundreds of megatons. So like some millions of tons of hundreds of millions of tons on TNT. Like you take maybe 100,000 of Hiroshima bombs together, that's one hydrogen bomb. Okay, guys, so probably let me finish on this today. So thank you for your attention. Let us hope for the situation to get better. It's completely unacceptable with the war waged against civilians on our eastern border of sovereign country, Ukraine. So we need to be supportive as much as we can. It's a pretty complicated situation because no one knows what it will lead to towards a nuclear war that everyone wants to avoid, because it will be complete disaster for the whole civilization. But let's hope that the situation will resolve and this unjustified Russian aggression will come to an end. So thank you again for your attention here. And if you have any questions, I will remain here for a few minutes to answer. Goodbye.